Hi, Jincho, can you hear me?
Yes, I can hear you.
All right,
I'll check
good.
from the with the PC.
Okay, we're ready. We're set and ready. I could see your screen for a minute, but not anymore.
Yeah, I just tested from the PC. It seems so.
There we go.
I like the
Morning.
background behind you.
Thanks. I did that on purpose. So just to inform the ones that don't know, the attendees are not allowed to join until exactly 10.
Tokyo,
Yes.
as what we did last time, maybe you can use the chat room to ask to answer some question.
Yeah, sure.
Nice.
Hopefully, BJ can join too.
He accepted the invite, so I'm assuming he will join.
Sure. Okay, good. Which, are you going to share your screen or you want me to
Oh.
screen my screen?
I thought you were gonna do the.
Okay.
Yeah. That way you can control your pace. There we go.
Good.
Yes. Looks good.
Hi.
My name is Ken.
Okay, I'll talk. You're visiting something? Yeah, I have a webinar, so I'll take this.
All right. Almost showtime. All right. Hello, everyone. Welcome to the webinar today, where we will learn how to build AI-powered robots with TI's new robotics SDK. We will wait a couple minutes while more people join. Hello, everyone that's joining. We are waiting one more minute while more people join, and we will get started. All right, well, let's get this show on the road. Welcome, everyone, to Build AI-Powered Robots with TI's new Robotics SDK. My name is Josue Samitis Ayala. I'm a product marketing engineer for Texas Instruments. And we will have a presentation by Dr. Junshul Rao. It's our senior systems architect for Edge AI and robotics. Moving on to our agenda. We will have a quick recap of what we have done in the robotics space here at Texas Instruments, and then Dr. Junshul Rao will go over the robotics SDK. He will go over some example reference designs in the SDK, and we'll follow up with a demonstration, live demonstration. I'm very excited to show how TI can help you build AI-powered robots using open source community platforms in a robotics SDK. These demos have been enabled on the low-cost open source Scuttle robot platform as shown here on the first picture, which is very low cost and you can obtain a base kit for under $500. Next, you can see how we can make a robot smarter by using AI in an object following demo using a single USB camera. We can go a step further and enable autonomous robots by using different sensor modalities like a stereo camera for 3D perception as seen on the third picture, as well as SLAM, which is simultaneous localization and mapping using 2D LiDAR, as well as a radar safety bubble demo using 4 radar sensors in the bottom middle. Finally, if you have our processor starter kit and are waiting for the rest of your sensors to be delivered, you can always run an object detection and classification demo using a Gazebo 3D robotic simulation, where you can drive around a digital version of the Scuttle robot using your keyboard. You can learn all about these demos and more with our new Robotics Academy, which you can get there by entering the address seen at the bottom of the screen, the ti.com/robotics academy. Now let's take a look at what powers all these robotic demos from Edge AI and how you can get started evaluating our processor today with no cost and low cost tools. Our ecosystem is geared towards helping you develop your application in a simpler, faster, and affordable way. On the first pillar here, you can see a block diagram exhibiting the TDA4VM processor with 8 TOPS of accelerated deep learning performance. The sophisticated multi-core processor includes dual ARM Cortex-A72s, a DSP core along with an AI accelerator, vision and imaging accelerators, as well as an integrated MCU island with a dual Cortex-R5 cores capable of achieving SIL3 safety standard if needed. There is a multimedia accelerator along with GPU for display as well. And it also includes a very rich peripheral set, including CSI 2 ports, an Ethernet switch, and a PCIe switch. This highly integrated SoC helps you design your systems affordably and simply by reducing the need of external components in your system. To help you take advantage of this SoC and all its power, we have provided open source tools and resources on both the hardware and software side, as you can see in the next 2 pillars. We have encapsulated the programming of these accelerators and cores with industry standard APIs mentioned here on the third pillar. And we also have a free online cloud tool, which you can simply visit by using your browser to access an EVM from a remote EVM farm and use one of the available deep learning models. You can also bring your own model, and you can experience the AI development and deployment on our hardware. You can do all this and run an inference all under 5 minutes. This is a great place for you to start your AI development. On the hardware side, we have multiple platforms available for you to experience this development environment. There's the TDA4VM starter kit now available on ti.com for less than $250, as well as the brand new BeagleBone AI64 single board computer that's around $189. And this board recently won Best in Show at Embedded World Conference in Germany. We also have a robotics purpose SOM by Technician, and this will be available on their website very soon. Now, all of these resources are available for you on ti.com/edgeai to get started, including links to our third-party ecosystem for camera, hardware, and software support. This is the one-stop shop for all the resources you need to get started. Now I will give the microphone to my coworker, Junchul. He will continue with the presentation. If we have time, we will take questions at the end. Otherwise, feel free to put in your questions in the chat. But first, let's do a poll. We would like to find out how we can help you. 1 second. Okay, we're experiencing some technical difficulties. I'm not able to pull up the poll, but feel free to enter your answers into the chat window. You can continue, Jinchul.
Sure. Um, I'll go through robotics SDK, especially software architecture side first, and go over some of the example reference design that is available in the SDK, and at the end I will do some live demo. So if you look at the slide here, this trying to summarize the the conceptual idea, how we make a Robo SDK and to make it easy to use. And ROS is a very popular developing platform for robotics application. So TDA4 is also very powerful. It has a multiple ARM core and deep learning, specialized deep learning, the core and the hardware accelerator and the DSP core and the multiple ISP and the vision accelerator. So using learning ROS on TDA4, you can, the way we pick is the Docker-based approach. In the diagram here, it's a red box representing Docker container. So normally a Docker container runs normally on ARM core, and it is typically isolated from the other DSP core and hardware accelerator. The challenge in the first when you develop the Robo SDK was this basically how to access all the hardware the DSP core and then hardware accelerator from inside a container. So the solution after more than a year of the development, the solution is this. So basically we already have a TI OpenVX, meaning the OpenVX framework, which is royalty-free open source framework for especially to access all the vision or deep learning hardware accelerator, and try to leverage all the software and hardware facility, and trying to connect with the ROS framework in the Docker container. So we start using the OpenVX and ROS framework in the Docker container. That is the first direction I want to highlight here. And then, for example, in this diagram, let's say we have a multiple ROS node up and running in the container. Most of them is running on ARM core. And some of them, for example, deep learning or vision chain can be accelerated on our hardware accelerator and the DSP core. To do that, what we do is we develop the OpenVX graph here, which is running on the Linux host Linux system, and then basically we provided some pass-through from the container. The way we do is we provide some the TI optimized vision application library and the deep learning library. We will get to some more detail in the next slide. So here in the similar graph, I mean, similar diagram, you can see, sorry. So here the TI Vision App library is already deployed on the Process SDK Linux for Edge AI. It's available on the SD card pretty much for the TDA4 device. And we provide a shared library we call the TI Vision library, which contains all the facility pretty much, which include the TI OpenVX infrastructure and kernel graph level APIs, which is useful for developing the deep learning and vision application, especially also robotics application as well. So which this allow the performance optimized application on TDA4. For example, you can upload or accelerate the compute intensive software block on C7, which is the latest DSP core, and MML, which is the hardware accelerator for the deep learning, which stands for matrix multiplication accelerator. And also we have a C6 DSP and bunch of hardware accelerator as I said, using OpenVX framework. But and the user perspective, because we provide most of the useful building blocks and the package into the vision application, so user can use the application that is available in the library. And this is the latest software architect, which is, as said, this is the, we have a Docker container, or we have Ubuntu-based Docker container. Right now we are using Ubuntu 20.04, and there we installed the ROS, two different distro. One is the ROS 1 and the other for the ROS 2. We provide two different Docker file pretty much for each of the ROS 1 and ROS 2. And then, for example, if the user can develop, if your user wanna develop the robotics application in ROS framework, most of the thing can be done like open source, for example, using OpenCV, TCL, G2 library. And let's say if you have a deep learning chain or vision application chain, you can use all the library that we provide, which is represented in the blue box here, which include OpenVX kernel and libraries. And as said, we have vision application library, and we also include the open source of deep learning runtime libraries. We support all the three popular runtime library: ONXRT and the TensorFlow Lite runtime, and Neo AI DLL libraries. And also in the SDK, basically we provide a ROS 1 and ROS 2 development environment in the Docker container. And also recently we provide the GStreamer plugins, which is already provided as part of the Edge AI offering. Most of all the plugin, which is optimized on TDA4 architect, is also available inside a robotics SDK container. And we also provide in the SDK the software building block and reference design that is optimized on TDA4 architect. So this is the typical example. One of the typical examples that you can use robotics SDK in your when you're developing the optimized robotics signal processing chain. For example, in this diagram, again, this box represents the Docker container, which is running on the TDA4. And let's say in this example, we have a stereo camera, which is connected to the USB 3 port. And the first node is the camera capture ROS node. Actually, we provide the ROS node for the jet camera. And then in the following chain, let's say we have a deep learning for the object detection and semantic segmentation and other post-assessment and other things. Can be uploaded on our C7 MMA and DSP and hardware accelerator through Vision Application Library and or deep learning runtime libraries. And then the post-processing can, for example, can run on the ARM core using, for example, the open source library, which include the OpenCV and the PCL, other libraries as well. And then the ROS natively, support all the deployment on the different machine. So we are leveraging in the reference design. For example, in this figure, in the visualization can happen on the another machine, Ubuntu PC in this case. And target and Ubuntu PC is connected or by Ethernet or Wi-Fi. So this allow, this architect allow mix and match APIs from the TI's Vision libraries and from the open source library, and which allow the differentiated custom and application TDA4. And we recently released the Robotics SDK 8.4, which is more like 1.1 version, but we decided to follow our process SDK's version number. So it's relatively new, but it already contains a lot of good stuff. For example, all this, for example, the 8.2, we released the stereo disparity, stereo vision processing as a ROS node. You can use it for other projects. And also we have a Vision CNN chain, which include the semantic segmentation and the 2D object detection. And then we have the 3D obstacle detection, the reference design, combined by leveraging the semantic segmentation and the stereo chain. And we recently released another 3D perception reference design, which now combine the 2D object detection with the stereo disparity map. And also, we have some of the reference design for localization mapping. And for example, the LiDAR-based 2D SLAM, which is open source. To give an example, most of the open source ROS package can apply learning on TDA4. And we have some optimized ORB SLAM, but it's not part of the SDK yet because of the licensing issue. And also we have the visual localization demo, which is everything is available in Robotics SDK 8.2. It's ready to evaluate. This table summarizes some more detail. So the first part, upper part, represents sensor drive and tools that are available in the Robotics SDK. First section is the camera driver. We are supporting the jet stereo camera. We provide the capture node. And also we provide a tool for the stereo camera, which include the stereo camera calibration tool. Another one is the remap. LDC is a lens distortion correction, we have other accelerator for the lens distortion correction. So we need to generate a lookup table for the LDC. We provide a tool for that. And also we provide the two camera capture node for the mono camera. One is based on OpenCV video capture node. The other one is recently we released the GStreamer based capture node. Also, we in the 8.2 we released ROS driver for TI's millimeter wave radar, which support 608043. So you can hook up the multiple millimeter wave and then generate the point cloud from the radar sensor and then process. And then the following, this is I already explained all the reference design and the process chain. And also, if you look at the column, this is we said that we provide all the implementation in ROS1 container and ROS container. This is all the combination you can see that we are supporting right now. So moving on to the some example reference design. The first one is I want to highlight the stereo processing chain. Again, this reddish box represents the Docker container, which include the ROS1 ROS Noetic engine and Ubuntu 2004, and some of the OpenCV and other open source library, the stuff. And in this case, we are using the stereo camera again, and as said, we provide a jet capture node here. And also the input side, we provide a different input. We provide the raw spec file, and also you can hook up as shown in the diagram. You can hook up the live stereo camera. And then this box start with the subscribe and the publisher is the ROS node, and that is optimized on our GDA4 hardware accelerator in this case. So start with the lens distortion compensation. We have a hardware accelerator, so it takes the UY/VY format and convert after doing all the remapping lens distortion compensation. The output format is ND12 format, and then hook up to the stereo disparity engine, and also depending on the option, the algorithm is using the multi-scalar hardware accelerator as well. So everything is accelerated. And then followed by the point cloud generation. The stereo engine published as if you look at the right side of figure, this is the upper left one is the confidence map, and right upper side is the disparity map. From this information, we can generate the XYZ point cloud information for each pixel, right? So this can be done on the C6 DSP or ARM core right now. And then I said this is the ROS driver. It published the disparity map and confidence map or the XYZ point cloud data. And then visualization happen on the remote visualization PC in Alvis. As said, all the compute intensive block is accelerated on our hardware accelerator in this reference design. And as said, SDK also provide the tool for stereo camera calibration, lookup LDC remap lookup table generation. So next reference design is the Vision CNN inference ROS node. So again, let's start with in this case, it pictures stereo camera, but you can swap with the mono camera or RAW spec as well. And it starts with the camera capture node as before. And this big box represents the optimized Vision CNN ROS node. And the point is everything is a hardware accelerator optimized on the TDA4 architecture. So as said, it's similar. This is a pre-processing chain for it's the main the deep learning is in this block. The deep learning using the deep learning runtime, and you can pick the different model. All the model is available on the Edge model. We have almost literally 100 ready to use AI model, which is already we call the model compilation. We convert all the thing in to the binary, and model artifact is ready to use on the TDA4. So LDC and MSSC and the pre-processing, which is sometimes doing the normalization for the deep learning model, subtracting the mean and apply the scaling. And I want to highlight this deep learning core is we are leveraging the DL Inference class, which is implemented already on the Edge AI, TI Edge AI. And this single ROS node actually supporting very, very versatile. That means you can swap the model of most of all the semantic segmentation and object detection model that is available in the TI Edge AI model zones, which is you have a lot of choice. So in this case, this is we picked the YOLO V3 in this example. And also, as said, this inference class supporting all the three major deep learning runtime libraries. And next reference design is the one example, and the adding of the two building block and using two building blocks that I presented before, and adding this blue, I mean the red ROS node, which is doing fuse together, combine the two information from the two low-level process chain to do the 3D perception. Let's go through the diagram some more detail. So in this case, stereo chain is being used, stereo camera is being used, and we have a capture node. And this is exactly same the stereo processing chain, same the ROS node that I presented before. And then the bottom one is the Vision CNN inference ROS node that just present. And the output is we have output tensor as a topic. And as said, from the stereo chain, we have a disparity row, which is 16-bit, which include the 13-bit disparity information, and then 3-bit for the continuous information. So this new ROS node is relatively simple. So this is pretty much the output. If from this figure represent the disparity map from the stereo engine, and the bottom one is from the 2D object detection, YOLO V3, for example. And then try to associate the two information. And in this reference design, try to get the XYZ information around the center of the bounding box. And in this visualization, actually, I convert to the range information. But I mean, the output tensor information from this object range ROS node actually contain XYZ information. and do the visualization on the PHS before. And that is the associated XYZ information is one of the goal. And second purpose of this new ROS node is generating the point cloud that is shown in this spot, right side, to provide a bird's eye view of the environment, pretty much. Because this is the motivation is like this: 2D bounding box detection cannot detect, in this case, wall and other obstacle. That is not because it is not part of the training, right? So, but I mean, robot need to understand the location of the wall and then some other object that is not probably is not detected by the CNN chain. So that's why we decide to generate the point cloud in this case. So the idea is quite simple. So scan the horizontally this battery map and generate the point cloud, and it's generate more like a LiDAR-based point cloud. That is the main purpose, but using the single sensor. Let's and this is the end of the. Maybe I'll go through some in live demo in the most of this reference design soon, and I'll briefly touch ROS2 support. As said, that in robotics SDK provide the Docker container environment for the ROS1 and ROS2. ROS2, because we are right now using 1804 container, we have a choice. So ROS2 Foxy or Galactic. Right now we install in the container Foxy right now, but it's very easy to migrate to the Galactic. And the ROS2, as you know, they are using the DDS, data distribution service. And we installed the two popular DDS. One is the eProxima Fast DDS and the Eclipse Cyclone DDS, which is already installed in the container. And then this table summarizes the default DDS selection on target and the visualization PC. Somehow we try the different combination. Somehow this gives the best smooth visualization on the PC. But you can easily switch the different DDS by using the single environment variable, which is this. Maybe can you go ahead, data polling?
Yes. Unfortunately, we had technical difficulties with the poll feature, but if you don't mind entering your answers on the chat, it will still help us come up with new demos and newer ways to help you in the future. Otherwise, you can move on, Junchu, to the live demonstration.
Okay. Yeah, I'll show my Ubuntu PC right now. Okay. So I'll go with the online documentation for robotics SDK. So we'll share the link for this. It contains all the detail about how to set the robotics SDK and all the details on each of the ROS node and the reference design. I'll do some demo for the ROS one first. So, and this terminal on the right side is on the target side. This is a UART on the bottom. So in the first, So we need to identify the the IP address that is assigned to the target, and this website terminal is the Ubuntu PC side. So I have config just checking the IP address, and I already set it up everything because this is being used to set the ROS master and ROS client setting, network setting. And this is a SH terminal to the terminal, right? To the target side. And then if you set up, or if you run the setup script, you create the J7 ROS home directly here, and then you can generate the script. For example, make a scripts ROS version. And it generate the two script, one for building the ROS, the Docker image, another for run the Docker images. So I already built the Docker images already. Let's check. So look at this. The bottom one is the 2004 Ubuntu 2004 Docker images, and this is the ROS Noetic Docker images, and this is a ROS 2 proxy Docker images. So I'll go into the Docker 1 container. Okay, and if you, basically, you can follow all this first section of the documentation. For example, I already built all the ROS node, Kekinate thing here, running this step before, so it's ready to run all the demos. And there is one table which is summarize all the launch file command in one single page. I will use as a cheat sheet for now. So I just connect the mono camera to the EVM, and so I'll do the object detection demo. So I need to use this. And it basically using the GStreamer based capture node in this example. And then run the Vision CNN inference ROS node. And then this is a left side, PC side. I already built the Docker images. In this, I have a lot, but it's already built in. And I already configured the IP address, and I have a aliasing here. I already, this is equivalent to the Docker run also. Okay, so let's check the basic stuff, ROS topic list, right? To see everything's published, right? So all the topic is coming from the target right now. This is actually Vision CNN output. Let's say, let's check actually this is published. Let's go. This is for each bounding box is generating bounding box information. It has 4 components, and it has XYZ information as well, and label information as well for each of the detected bounding box. And then I'll run the visualization ROS node on the PC. So this is the line. So this, maybe I'll use this one for my setup to explain my setup. So this is a Scuttle robot that I use for the 3D perception reference design development. And but to evaluate all the reference design that is available in the SDK, you don't need the scroll bar. You only need the escape board here and the live sensor, or you can use the raw spec file. In that case, you don't need the live sensor at all. And in this case, I set up the Wi-Fi and motor control board, everything, but I'm using purely these. I'm not using that part right now in this demo. So and this is a jet camera, and some demo we are using LiDAR sensor. Maybe so it detect. This is a YOLO V3, but you can easily switch different model. For example, I don't know, you can see or not. This is actually our code. So if you look at rows 1 part, and on the node we have all the rows node for the Vision CNN. This is the thing. There is a YAML file, the param, and also there is launch file. There's several of them. For this GSCAM object detection CNN. If you look at here, there is a DL model path which is pointing the model Joe. You can switch the different model. You can point, for example, if you turn on this one, you can use SFT model, for example. And there are a bunch of options. You can keep a try. Okay, so maybe I'll show the second demo using stereo camera in this case. I'll change the sensor right now. So I connect the jet camera right now. Let's see. I usually check the this devices recognize in the container or not. And then going back to the cheat sheet, I will show the 3D perception demo using jet camera as input. And then maybe I'll split the terminal. Or some other thing. I'll launch the visualization, which is so the learning. Maybe I'll show the compute graph. So I try to give you the compute graph. So as I said, this is capture node running on the target right now, running on ARM. And this SDE is also node, is about learning on the target using all the hardware accelerator. And this was a Vision CNN chain, the ROS node is a little bit big, but I mean, it's optimized on the C7 MMA and all the hardware accelerator. And this this is a visualization, which is learning small, learning on the PC right now is very, very tiny. And this is the fusion node. It's a small ROS node learning on the target right now. And they publish the bounding max information with the XY information. And this is for the visualization. This two node is for the visualization. Okay, this is the ROS1 demo. Maybe I'll briefly give the ROS2 demo, one of them. Okay. So I'll get out of the Docker container for ROS1, and I already built the ROS2, and I'll go into ROS2 container. I already built the thing, but in the different ROS workspace. Right now. Okay, so maybe I'll show the symmetric segmentation chain for the jet camera. I also need to switch the PC side. This is a kind of shock. So, oh, I need to source. So jet camera, this is a command line. This is a for visualization for the semantic segmentation. So this model was trained for outdoor data set. So a little bit of error here, but it's reasonably doing well. So this we can switch to the mono camera. In this case, I'm using stereo camera. Just processing just one of the one. I think using right side of the camera. Okay, maybe I'll go back to the slide.
Yes, please.
Yeah, I did.
Well, here we have our.
Jose, we can discuss the Q&A and last call for action.
I'm sorry.
Maybe you can take over from here.
Yeah, of course.
Do you have some question you want to discuss?
Yes. Do we have any questions from the audience? I first want to make this call to action for you to get started in your development. You can follow these links. We will post these slides online for you to download, and you can click on these links. You can go to ti.com/tools/skTDA4VM to get the starter kit. You can use our cloud tool as well from there, and yeah, we also have the robotics SDK linked. Most of these things are also linked in the Edge AI Robotics Academy, where you can learn about these demos and do hands-on coding. And as always, we have free support for you on E2E. Now I will try to unmute people so we can take on some questions, or you can also feel free to enter questions in the chat.
Jose, I think there's one unanswered question in the chat from the Gary Wu. He asked,
Oh,
what's the meaning for different color in the table? But I don't know which table he's talking about. I think maybe if we go back to the slide, maybe
In this
this one. Yeah, maybe
this one.
Yeah, I guess so. He asked
yes, I believe that
Gary.
was the slide.
Yeah, he
Oh,
asked
okay.
Oh,
meaning
okay.
of the color code.
Yeah, maybe this is a 8.4 release. The green one is that we released in the previous release, and the blue one is what we released in 8.2. That is what I mean. Basically, the blue one is what we newly released in 8.2 release, which was April timeframe. Did I answer your question, Gary?
Hello, is my audio coming in okay?
Yes.
I can hear you.
All right, my question is maybe to open up the millimeter wave or the radar topic, and I'd like to know what is the I guess problem statement that you think is most suited to be answered with radar sensors for researchers that are working with the mobile robotics and already working with your SDK.
Okay. So I mean, we closely working with the RadarView right now, and this is the first step. We just enabled the driver side first, and I think that in the pipeline we have some more projects in the pipeline. Some we see a good progress. For example, RadarView already implement the object tracker using the point cloud, and which is right now is running on the millimeter wave device itself, and then basically we try to update our ROS driver to publish the tracked object information as well as the point cloud information. That is one aspect right now.
So we at the Texas A&M University, we have a number of labs that are using LiDARs. They're using stereo cameras, but I don't see any that are using radar. And so if I wanted to encourage them to try out the radar sensor, what is the key use case, or what is the selling point to be using radar? And is it alternative to LiDAR, or is it do you recommend that it's in addition to LiDAR?
Yeah, so I can take that up. Right. So radar is really an technology in the automation space and automotive vehicle space, including robotics and the autonomous driving car or ADAS assisted car, where it complements the vision and the LiDAR sensors where they have their weak points. So radar is very good in detecting the objects in the dark where vision fails. It is very good in and the LiDAR fails, and it is very good in object tracking, and it is quite cheaper and less complex compared to 3D LiDAR. And it can also do a see-through detect an objects such as the glasses where vision or the LiDAR may fail. And it works very well in fog, smoke, and other conditions where other sensor modality fails. So it's a very competitive alternate sensing modality which helps either to complement the entire robustness of the system or to replace other existing or costly sensors such as 3D LiDAR, which are just not also costly but power hungry depending on the use cases. So typically, specifically for the safety obstacle detection, right? it's very, very popular there to complement it with existing sensor modalities, and then replacing entire SLAM functions as well via this, getting very popular. So I do highly encourage, if you are doing some advanced research program, to look into like radar technology.
That sounds great. Do we have enough time for you to elaborate on, you said it has a strength in object tracking in compared with camera and LiDAR, perhaps?
We have 1 more minute.
Okay, if there's any other questions, we can switch to the next.
Anybody?
Hey, David, we can take that question offline. I think they're
Okay.
on top of ours, right? So
Yeah, that sounds good. Thank you.
Well, thanks everyone for joining. Please visit ti.com/edgeai if you need any more information, and also visit ti.com/roboticsacademy to find out how you can do hands-on coding and try some of these demos yourself. Thank you.
Thank you.